Imagine a place where gravity is so intense, so utterly relentless, that nothing, not even light, can escape its grasp. A cosmic vacuum cleaner devouring everything in its path. We call them black holes, and they are, without a doubt, the universe's most extreme creation. But what exactly are these invisible titans? Imagine space-time, that fabric of reality Einstein so brilliantly described as a trampoline. Now, place a bowling ball in the center. That's a star warping the trampoline. Now, imagine an object so massive, so dense, that it punches a hole right through the trampoline, creating an infinitely deep well. That's a black hole. They are cosmic bottomless pits, where the known laws of physics seem to break down. Everything gets squeezed, crushed, and disappears. How heavy are they? Some are relatively small, only a few times more massive than our sun. But then there are the supermassive black holes, lurking at the heart of almost every galaxy, with masses equivalent to millions or even billions of suns. Our own Milky Way harbors one of these behemoths, a silent guardian known as Sagittarius, a star. These dark monsters bend space-time itself, creating gravitational distortions that defy our everyday intuition. They are cosmic mirages, bending and magnifying light from distant objects, offering us glimpses of the universe that would otherwise remain hidden. Is it a monster or just another force of nature? When you start thinking about a black hole in our solar system, it can get pretty scary. What if one of these gravitational beasts decided to pay a visit to our quiet corner of the galaxy? Black holes are not merely destructive forces. They play a crucial role in shaping galaxies, triggering star formation, and even distributing the very elements that make up our bodies. They are, in a sense, cosmic recyclers, taking the old and creating the new. But the most fundamental, the most tantalizing question remains. What happens when something crosses the point of no return, the event horizon? Does it simply vanish from our universe? Or is there something more, something hidden beyond that impenetrable veil? The answer to this question may lie at the very heart of existence, challenging everything we think we know about reality, space, and time. What's inside? That's what scientists all over the globe are trying to figure out. So what happens when the universe's ultimate garbage disposal is born? Where do these cosmic vacuum cleaners actually come from? The answer, surprisingly, is from the death of stars, but not just any star. We're talking about the heavyweights, the stellar giants, the ones at least 8 times more massive than our own sun. Think of these massive stars as cosmic forges, burning through their nuclear fuel at an incredible rate. They live fast, die young, and leave behind a spectacular mess. For millions or even billions of years, they shine brilliantly, fusing hydrogen into helium, helium into carbon, and so on, all the way up the periodic table to iron. But iron is where this party stops. Fusing iron doesn't release energy, it consumes it. Imagine a star's core as a pressure cooker, constantly fighting against the crushing force of gravity. Nuclear fusion is the fire that keeps the pressure up. But once that fire sputters out, once the star's core is choked with iron ash, the pressure drops and gravity wins. It's like pulling the plug on a cosmic bathtub. What follows is one of the most violent events in the universe, a supernova explosion. In a fraction of a second, the star's core collapses in on itself. The outer layers, no longer supported by the core's energy, come crashing down. These layers meet the incredibly dense core and rebound outwards in a shockwave of unimaginable power. Picture this. A burst of energy brighter than an entire galaxy, visible across billions of light years. A supernova is not just a pretty light show. It's a cosmic recycling event. The explosion scatters heavy elements forged in the star's core out into the surrounding space, enriching the interstellar medium and providing the raw materials for new stars and planets. In fact, the very atoms that make up your body were likely forged in the heart of a long-dead star and scattered across space by a supernova. You are, in a very real sense, stardust. But for the star itself, the supernova is the end of the line. Or is it? What happens to that collapsed core, that incredibly dense remnant left behind after the explosion? The answer depends on the star's original mass. For some, the core becomes a neutron star, an incredibly dense object where protons and electrons are crushed together to form neutrons. But if the star is massive enough, even the neutrons can't withstand the relentless pull of gravity. Gravity continues to squeeze, crushing the matter into an infinitely small point, a singularity. This is the moment of birth, the birth of a black hole. A new gravitational monster has emerged from the stellar ashes. It is an object from which nothing, not even light, can escape. It's a region of space-time where gravity reigns supreme, warping the very fabric of reality. Think of it as the ultimate cosmic trash compactor, crushing everything into an infinitesimally small volume. Everything that once constituted the star, all its mass, all its energy, is now concentrated at a single point. It's a mind-bending concept, one that pushes the limits of our understanding of physics. But how can something so small exert such a powerful gravitational pull? Well, the mass is still there, just concentrated in an incredibly small space. The more mass you pack into a smaller volume, the stronger the gravity becomes. It's like squeezing an elephant into a thimble. All that elephant is still there, just incredibly compressed. This new black hole immediately starts to flex its gravitational muscles, warping the space-time around it. It starts to draw in any nearby matter, slowly at first, then with increasing speed and ferocity. It's a cosmic feeding frenzy, and the black hole is the ultimate predator. So the next time you gaze up at the night sky, remember that somewhere out there a stellar giant has met its end in a blaze of glory, leaving behind a gravitational monster, a black hole ready to begin its reign of cosmic terror. What secrets does it hold, hidden beyond that invisible boundary? The quest to find out is only just beginning. And so a black hole is born, a cosmic leviathan ready to devour anything that gets too close. But what exactly does too close mean? Where does the point of no return actually lie? Imagine sailing the vast ocean and suddenly you see a waterfall, but not water is falling. The fabric of reality is falling into this hole. This brings us to one of the most fascinating and terrifying concepts in astrophysics, the event horizon. Picture a perfectly spherical boundary surrounding the singularity, an invisible membrane marking the edge of the black hole. It's not a physical barrier, you couldn't bounce a ball off it, but it is a point of no return. This boundary was first described mathematically by the German physicist Karl Schwarzschild just months after Einstein published his theory of general relativity. Schwarzschild's solution, as it became known, predicted the existence of these strange objects, regions of space-time so warped that nothing, not even light, could escape. It was a theoretical bombshell. It sounds like something out of a science fiction novel. Is this a fact? Yes. Think of the event horizon as the ultimate cosmic veil, separating our observable universe from the unknown interior of the black hole. It's a boundary that, according to our current understanding of physics, is absolute. Once you cross it, escape is impossible. It's as if you've stepped through a one-way mirror, forever lost to our side of reality. But why is this boundary so absolute? What makes it so inescapable? The answer lies in the relentless force of gravity. The closer you get to a black hole, the stronger the gravitational pull becomes. Near the event horizon, this pull becomes so intense that the escape velocity, the speed needed to break free from the black hole's gravity, exceeds the speed of light. And here's the kicker. According to Einstein's theory of special relativity, nothing can travel faster than light. So, if even light can't escape, then nothing else can either. It's a cosmic prison, from which there is no release. Imagine throwing a baseball into the air. The stronger you throw it, the higher it will fly. But what if you throw it so hard, it will never come down? The event horizon isn't just a theoretical construct, it's a real physical threshold. Its size depends directly on the black hole's mass. The more massive the black hole, the larger the event horizon. For a black hole with the mass of our Sun, the event horizon would be about 6 kilometers in diameter, around 3.7 miles. For supermassive black holes like the one at the center of our galaxy, the event horizon can be larger than our entire solar system. Crossing the event horizon would be a truly mind-bending experience, or rather a non-experience, since you wouldn't be able to report back. You would effectively disappear from our universe, your fate sealed by the crushing gravity of the singularity. But what would you actually see or feel as you approached this point of no return? That's a question that has fascinated physicists and science fiction writers alike for decades. But imagine watching someone else fall in, from a safe distance, of course. As they approach the event horizon, you would see them slow down, their movements becoming increasingly sluggish. This is due to the extreme time dilation caused by the black hole's gravity. Time itself would appear to be stretching out as they get closer. They would also appear to become fainter and redder as the light they emit is stretched out and loses energy. Eventually, they would simply fade from view, their image frozen at the event horizon, a ghostly reminder of the object that once was. They would look like an insect stuck in a spider web. The event horizon is more than just a boundary, it's a gateway to the unknown. It's a place where our current understanding of physics breaks down, where the laws of nature as we know them cease to apply. What happens beyond the veil, inside the black hole? Does space-time continue to exist? What is the nature of the singularity? These are questions that continue to challenge and inspire scientists around the world. And perhaps somewhere in the answers to these questions lies a deeper understanding of the universe itself. But what awaits you, or rather what awaits anything unlucky enough to cross the event horizon? The answer is both terrifying and strangely elegant, a direct consequence of Einstein's revolutionary ideas. It is a phenomenon known as spaghettification. Yes, you heard that right, spaghettification. It sounds like something out of a bad science fiction movie, but it's a very real prediction of Einstein's theory of general relativity. So what exactly is spaghettification? Imagine you are falling feet first into a black hole. As you get closer, the gravitational pull on your feet becomes significantly stronger than the pull on your head. This difference in gravitational force, known as tidal force, is what causes the stretching. It is the same force that causes tides on Earth, but amplified to an unimaginable degree. On Earth, the moon's gravity pulls more strongly on the side of the planet facing it, creating a bulge of water, hence the high tide. Now amplify that force by a factor of, let's say, 1 billion, and you begin to get a sense of what happens near a black hole. Your feet are being pulled towards the singularity with tremendous force, while your head experiences a weaker pull. This difference stretches you out vertically like a piece of taffy being pulled in 2 directions. But that's not all. While you're being stretched vertically, you're also being compressed horizontally. The gravity of the black hole is squeezing you from the sides, compressing you into an ever narrower shape. The result? You are stretched and squeezed into a long, thin strand resembling a cosmic spaghetti noodle. This isn't a gentle process. The tidal forces near a black hole are so extreme that they would tear apart any object, no matter how strong. Imagine a spaceship venturing too close. First, it would start to creak and groan under the immense stress. Then, rivets would start to pop, hull plates would buckle, and the entire structure would begin to elongate. Soon, the ship would be ripped apart, atom by atom, its constituent molecules scattered into the swirling chaos around the black hole. It would be as if the universe itself was unraveling the very fabric of the vessel. But it's not just spaceships that face this gruesome fate. Even something as resilient as a neutron star, one of the densest objects in the universe, would be torn apart by spaghettification if it strayed too close to a black hole. The immense tidal forces would overcome the star's internal gravity, ripping it apart and adding its matter to the black hole's ever-growing accretion disk. What about a human being? Well, the experience wouldn't be pleasant, to say the least. Long before you were reduced to a stream of subatomic particles, you would be subjected to unimaginable pain and suffering. Every bone in your body would be stretched and broken, your organs would be crushed, and your nervous system would be overwhelmed. It would be a truly horrific way to go. The size of the black hole matters too. For a smaller, stellar mass black hole, this spaghettification process would begin far outside the event horizon. You would be torn apart well before you even crossed the point of no return. However, for a supermassive black hole, the event horizon is much larger, and the tidal forces are weaker at the event horizon. It is theorized that it might be possible to cross the event horizon of a supermassive black hole without immediately being spaghettified. You might even have a few moments to observe the bizarre and distorted reality inside before being inevitably crushed by the singularity. A truly once-in-a-lifetime experience, although a very short one. Is there anything that could survive this cosmic shredder? Perhaps something composed of hypothetical exotic matter, something with negative mass or repulsive gravity. Theoretical physicists have explored such possibilities, but so far no such substance has been found to exist. As far as we know, everything that falls into a black hole is ultimately destined to be stretched, squeezed, and ultimately consumed. A reminder of the raw power that lies hidden within these cosmic behemoths. What happens to the information of everything that fell into the black hole? That mystery will take us deeper into our journey of black hole investigation, but even that cosmic spaghettification is just the prelude to the main event. What truly lies beyond the veil of the event horizon? What happens to all that matter, all that energy, once it crosses the ultimate point of no return? Prepare yourself, because the answer takes us to the very edge of known physics, to a place where space and time become utterly alien. We're talking about the singularity, an infinitely small point where all the mass of the black hole is concentrated. Think of it as the ultimate cosmic crush, a point of zero volume and infinite density. It's a concept that strains the very limits of our imagination. Can you picture something that has mass but occupies zero space? It's like trying to fit the entire universe into a grain of sand and then crushing that grain of sand down to nothing. Here, at the heart of the black hole, our current understanding of physics simply breaks down. Einstein's theory of general relativity, our best description of gravity, predicts the existence of these singularities, but it also predicts its own failure. The equations become infinite, nonsensical. It's as if the universe is throwing up its hands and saying, "I don't know what's going on here anymore." What does it actually mean for our current physics to be inadequate? Imagine you are an engineer trying to build a bridge, but your materials suddenly lose all their strength. You can no longer predict how they will behave under stress, and your entire design collapses. Similarly, at the singularity, our fundamental laws of nature crumble, leaving us without a reliable framework to understand what's happening. Some scientists believe that the singularity is not a physical object, but rather a sign that our current theories are incomplete. It could be that a new theory of quantum gravity, a theory that combines general relativity with quantum mechanics, is needed to fully describe what happens at these extreme conditions. Perhaps the singularity is not a point at all, but some other exotic structure that we cannot yet comprehend. But what is space and time like inside this ultimate prison? Does space-time even exist in the same way that we experience it? One possibility is that the singularity represents a tear in the fabric of space-time, a gateway to another dimension, or even another universe. It's a mind-bending concept, one that has fueled countless works of science fiction. Or could it be that inside a black hole, space and time switch roles? What we perceive as space becomes time, and what we perceive as time becomes space. Imagine traveling not through space to reach the singularity, but traveling through time, hurtling inexorably towards the future. Would the laws of cause and effect still hold true? Consider this. If you could somehow survive the spaghettification and the extreme tidal forces and cross the event horizon of a supermassive black hole, what would you actually see? Would it be a blinding flash of light, a swirling vortex of energy, or simply utter darkness? Or maybe even nothing at all? The truth is, we don't know. The inside of a black hole is the ultimate unknown, a region of space-time so extreme that it defies our current understanding. It's a cosmic laboratory where the fundamental laws of nature are being tested to their limits, and perhaps by studying these enigmatic objects, we can gain a deeper understanding of the universe itself. As we continue to peel back the layers of this cosmic onion, what more astonishing revelations await us? But even that cosmic spaghettification is just the prelude to the main event. What truly lies beyond the veil of the event horizon? What happens to all that matter, all that energy once it crosses the ultimate point of no return? Prepare yourself, because the answer takes us to the very edge of known physics, to a place where space and time become utterly alien. We're talking about the singularity, an infinitely small point where all the mass of the black hole is concentrated. Think of it as the ultimate cosmic crush, a point of zero volume and infinite density. It's a concept that strains the very limits of our imagination. Can you picture something that has mass but occupies zero space? It's like trying to fit the entire universe into a grain of sand, and then crushing that grain of sand down to nothing. Here, at the heart of the black hole, our current understanding of physics simply breaks down. Einstein's theory of general relativity, our best description of gravity, predicts the existence of these singularities, but it also predicts its own failure. The equations become infinite, nonsensical. It's as if the universe is throwing up its hands and saying, I don't know what's going on here anymore. What does it actually mean for our current physics to be inadequate? Imagine you are an engineer trying to build a bridge, but your materials suddenly lose all their strength. You can no longer predict how they will behave under stress, and your entire design collapses. Similarly, at the singularity, our fundamental laws of nature crumble, leaving us without a reliable framework to understand what's happening. Some scientists believe that the singularity is not a physical object, but rather a sign that our current theories are incomplete. It could be that a new theory of quantum gravity, a theory that combines general relativity with quantum mechanics, is needed to fully describe what happens at these extreme conditions. Perhaps the singularity is not a point at all, but some other exotic structure that we cannot yet comprehend. But what is space and time like inside this ultimate prison? Does space-time even exist in the same way that we experience it? One possibility is that the singularity represents a tear in the fabric of space-time, a gateway to another dimension or even another universe. It's a mind-bending concept, one that has fueled countless works of science fiction. Or could it be that inside a black hole, space and time switch roles? What we perceive as space becomes time, and what we perceive as time becomes space. Imagine traveling not through space to reach the singularity, but traveling through time, hurtling inexorably towards the future. Would the laws of cause and effect still hold true? Consider this. If you could somehow survive the spaghettification and the extreme tidal forces and cross the event horizon of a supermassive black hole, what would you actually see? Would it be a blinding flash of light, a swirling vortex of energy, or simply utter darkness? Or maybe even nothing at all? The truth is, we don't know. The inside of a black hole is the ultimate unknown, a region of space-time so extreme that it defies our current understanding. It's a cosmic laboratory where the fundamental laws of nature are being tested to their limits. And perhaps, by studying these enigmatic objects, we can gain a deeper understanding of the universe itself. As we continue to peel back the layers of this cosmic onion, What more astonishing revelations await us? Let's hone in, focusing all of our attention on this core, this enigmatic entity, the singularity. Mathematicians predict this to be a place of zero volume, yet possessing infinite density. It's a concept that's not just difficult to grasp, it's mathematically challenging, leading us to question some of the very foundations of our understanding. Are we perhaps staring at the limits of Einstein's magnificent creation, his theory of general relativity? Think about this. Einstein's work, groundbreaking as it was, revolutionized our perception of gravity, space, and time. His equations elegantly predicted black holes, and they've held up remarkably well under a century of scrutiny. But here at the Singularity, they falter. The math just doesn't work anymore. It's akin to discovering that the map you've been using to navigate the world suddenly becomes blank as you approach the most interesting location. Is the Singularity a real physical thing? A point of infinite density crammed into zero space? Or is it a signpost, a cosmic warning flare telling us that we need a new, more comprehensive theory? Perhaps a theory that unifies general relativity with the quantum world, a theory of everything. Consider the implications if the singularity isn't what we think. What if it's not a point, but some other, more complex structure hidden within the black hole? Some physicists speculate about exotic possibilities like tiny wormholes, baby universes, or even connections to other dimensions. It sounds like science fiction, but the math leaves the door ajar for these possibilities. Maybe, just maybe, the singularity is not the end of the story, but a beginning, a gateway to something beyond our current comprehension. Perhaps the universe is far stranger, far more interconnected than we ever imagined. As we continue to probe the secrets of these dark behemoths, perhaps we're not just unlocking the mysteries of black holes, but we're unlocking a deeper understanding of reality itself. But is that it? Is that all there is to the story of a black hole? An infinitely dense point where the laws of physics simply vanish? What if the key to unlocking this cosmic puzzle box lies not in looking at the singularity, but in understanding the very framework that predicted its existence in the first place? The game changer, the revolution, the mind bender known as Albert Einstein's theory of general relativity. Forget everything you think you know about gravity. It's not just some invisible force pulling you towards the Earth. According to Einstein, gravity is something far more profound, more fundamental, more intertwined with the very nature of reality. Imagine space-time, the fabric of the universe, as a vast, four-dimensional stage where all events unfold. Now, imagine massive objects like planets, stars, and, yes, black holes, as actors on that stage. Einstein told us that these massive objects don't just sit there. They warp and curve the fabric of space-time around them. It's like placing a bowling ball on a trampoline. The ball creates a dip, and if you roll a marble nearby, it will curve towards the bowling ball, not because the bowling ball is pulling it, but because the trampoline itself is curved. That curve, that distortion of space-time, that is what we perceive as gravity. The Earth orbits the Sun not because the Sun is pulling on it, but because the Sun is warping the space-time around it, creating a sort of cosmic slide that the Earth follows. An object as large as our Sun bends the fabric of our reality on a cosmic scale. Now take an object 1,000,000, 1,000,000,000, even 1,000,000,000,000 times more massive than our Sun, and the scale of what it can do to space-time is almost unimaginable. So, where do black holes fit into all of this? They are the ultimate expression, the most extreme manifestation of Einstein's warped reality. They are objects so massive, so dense, that they create a gravitational well so deep, so steep, that nothing, not even light, can climb out. It's as if they've punched a hole right through the fabric of space-time, creating a cosmic abyss. Think of it like this. If a planet is a small dimple on the trampoline, and a star is a deeper bowl, a black hole is a bottomless pit, a tear in the very fabric of the universe. a cosmic monster made of gravity. It's this extreme warping of space-time that gives black holes their bizarre and mind-bending properties. From the event horizon to spaghettification, it all stems from Einstein's genius. But here's the truly remarkable thing. Einstein developed his theory of general relativity over a century ago, long before we had any direct evidence that black holes even existed. He was working purely from mathematical principles, from a desire to understand the fundamental nature of gravity. It's as if he had built a map of a land he had never seen, and that map turned out to be astonishingly accurate. How did he accomplish this? His theory was born from thought experiments, complex mathematical equations, and a relentless pursuit of the truth. Could he have imagined, back then, the implications of his work? Did he foresee that his theory would not only predict the existence of these cosmic beasts, but also provide the very foundation for understanding their hidden interiors? Now, it's true that Einstein's theory breaks down at the singularity, but it's also true that it's the only framework we have for even approaching the question of what's inside. His insights are the flashlight we use to peer into the darkness, the ladder we climb to reach the unknown. His vision laid the path to exploration of these cosmic titans, and to this day, scientists use his theory to better grasp black holes. Without Einstein's work, we would be lost in the dark, unable to even begin to comprehend these enigmatic objects. He gave us the language, the tools, the very questions to ask. It's a testament to the power of human intellect, the ability to unlock the secrets of the universe through sheer force of thought. General relativity is a mind trip, a paradox, a masterpiece. And even more paradoxes await us. What if I told you that we can actually see these invisible monsters? We can, and we will. Einstein's theory painted a picture of gravity unlike anything humans had conceived before. It opened the door to understanding how these cosmic vacuum cleaners, these black holes, warp the very fabric of existence. But if light itself cannot escape, how can we possibly hope to study these invisible behemoths? Are they doomed to remain forever hidden, shrouded in an impenetrable cloak of darkness? The answer, as often happens in the world of science, lies in ingenuity, in finding clever ways to observe the unobservable. Astronomers are like cosmic detectives, piecing together clues from the faintest signals, the slightest distortions in the universe around us. One of the most powerful tools in their arsenal is the ability to observe the effects black holes have on their surroundings. Consider a binary star system where two stars are locked in a gravitational dance around each other. If one of those stars suddenly vanishes, collapsing into a black hole, what happens to its companion? That companion star will continue to orbit, seemingly around nothing, but its motion will betray the presence of something massive, something unseen, pulling it along its orbital path. By carefully measuring the star's velocity and its distance from the invisible object, astronomers can calculate the mass of this dark companion. If that mass exceeds a certain threshold, several times the mass of our Sun, then the evidence points strongly towards a black hole. It's like watching a ghostly figure waltzing with an unseen partner, their movements revealing the presence of a hidden dancer. But this is not the only way these cosmic phantoms give themselves away. In many cases, black holes are not solitary wanderers. They exist in crowded regions of space, surrounded by gas and dust, the leftovers from stellar explosions, or the detritus of disrupted galaxies. As this matter spirals towards the black hole, it forms a swirling disk, a cosmic whirlpool known as an accretion disk. Now, imagine the friction within that swirling disk, the particles of gas and dust rubbing against each other at incredible speeds. This friction generates immense heat, temperatures soaring to millions of degrees, far hotter than the surface of any star. This superheated matter glows fiercely, emitting a torrent of radiation across the electromagnetic spectrum, including powerful X-rays. These X-rays, which are like a cosmic cry from the edge of oblivion, can be detected by telescopes orbiting high above Earth's atmosphere. They act as a beacon a telltale sign that a black hole is lurking nearby, feasting on its cosmic meal. It's like finding the glowing embers of a fire, revealing the presence of a hidden inferno. One prime example lies in the constellation Cygnus, where we find Cygnus X1, one of the first black holes ever discovered. This object is a binary system, consisting of a blue supergiant star and a dark, unseen companion. The supergiant is constantly shedding gas, which is then drawn towards the black hole, forming a scorching hot accretion disk. The resulting X-ray emissions are so intense that they can be easily detected from Earth, providing compelling evidence for the existence of a black hole. What makes these X-ray emissions so important? Well, they provide a direct window into the extreme environment surrounding the black hole, allowing astronomers to study the behavior of matter under conditions that are impossible to replicate on Earth. They can measure the temperature and density of the accretion disk, track the motion of gas as it spirals inwards, and even probe the effects of the black hole's powerful gravity on the surrounding spacetime. Accretion disks can be spectacular to observe. They can be as wide as our solar system, and they emit so much energy that they can outshine the combined light of billions of stars. They act like cosmic lighthouses, guiding astronomers to the location of these otherwise invisible objects. Consider the supermassive black holes at the centers of galaxies. These behemoths, millions or billions of times more massive than our Sun, often have vast accretion disks surrounding them. As matter falls into these disks, it generates enormous amounts of energy, powering quasars, some of the brightest objects in the universe. A quasar is like a cosmic fireworks display, fueled by the black hole's endless appetite. Scientists have discovered that the brightness and variability of quasars can be used to measure the mass and spin of the black holes at their centers. It's like listening to the roar of an engine to determine its size and power. The faster the engine roars, the bigger and more powerful it is. But it's not just X-rays that can reveal the presence of these cosmic phantoms. Astronomers also use other wavelengths of light, from radio waves to infrared radiation, to study black holes and their surroundings. Each wavelength provides a different piece of the puzzle, helping to build a more complete picture of these enigmatic objects. The radio waves can reveal the presence of powerful jets of particles that are ejected from the vicinity of the black hole at near light speed. Infrared radiation can penetrate through dust clouds, revealing the hidden structure of accretion disks. It's like using different types of light to illuminate a dark room, each revealing a different aspect of the scene. Now, none of this provides a direct view of the black hole itself, of course. We can't see past the event horizon, the point of no return. But by studying the indirect effects of these objects, by observing their gravitational influence on nearby stars, by detecting the radiation emitted by their accretion disks, and by analyzing the properties of quasars, astronomers have been able to confidently confirm the existence of these cosmic monsters. These invisible giants, once purely theoretical constructs, are now known to be real, to be abundant, and to play a crucial role in the evolution of galaxies. It's a testament to the power of human ingenuity, the ability to see the unseen, to unravel the mysteries of the universe through careful observation and brilliant deduction. And as technology progresses, we are poised to reveal more secrets of these elusive entities. What wonders may await us as we delve deeper into the mysteries that surround supermassive black holes? But these black holes we've been discussing, these stellar mass objects born from the collapse of individual stars, are merely cosmic gnats compared to the truly colossal residents of the universe. Prepare to journey to the heart of galaxies, to places where gravity reaches unimaginable extremes, to witness the reign of supermassive black holes. These aren't your average run-of-the-mill black holes. We're talking about gravitational behemoths, cosmic titans with masses millions, even billions, times that of our Sun. Picture our Sun, a star that could fit 1 million Earths inside. Now imagine an object with the mass of a billion suns. It is a truly mind-boggling scale difference. And where do these giants reside? Right in the very centers of most, if not all, galaxies, including our own Milky Way. At the heart of our galactic home, 26,000 light-years away in the constellation Sagittarius, lurks a supermassive black hole known as Sagittarius I star. While not currently devouring vast amounts of matter, it still possesses a mass equivalent to roughly 4 million suns. But how did these galactic leviathans come to be? The truth is, their origin remains one of the greatest unsolved mysteries in astrophysics. There are a number of leading theories, each offering a tantalizing glimpse into the possible formation mechanisms. One compelling idea involves stellar mergers, a cosmic domino effect of collapsing stars and accumulating mass. Imagine a dense cluster of stars, packed tightly together in the early universe. Over billions of years, these stars collide and merge, forming ever larger and larger stars. Eventually, one of these stellar behemoths reaches a critical mass and collapses, creating a seed black hole. This seed then continues to grow, gorging itself on the surrounding stars and gas, eventually ballooning into a supermassive giant. Think of it like a snowball rolling down a hill, gathering more and more snow as it goes, growing exponentially until it becomes an unstoppable force. The difference here is that the snowball is a black hole, and the snow is the stellar matter and the fabric of space-time itself. Another intriguing theory proposes the existence of primordial seeds, black holes formed not from stars but from the direct collapse of extremely dense regions in the very early universe. These primordial black holes, if they exist, would have formed just moments after the Big Bang, when the universe was still incredibly hot and dense. They would have acted as seeds, gravitationally attracting matter and growing into the supermassive black holes we see today. It's like planting an apple seed and waiting for it to grow into a tree. These primordial black holes would be the seeds of the galaxies, and the galaxies themselves would be the trees, growing from the black hole's foundation. There's even a third theory that goes something like this: massive gas clouds collapsing directly into black holes. In the early universe, vast clouds of gas existed that were much larger than anything that exists today. Because these clouds were so massive, they would at times spontaneously collapse into a supermassive black hole. The birth of supermassive black holes is a puzzle that scientists are determined to solve, and the study of these objects may lead to insights into not only their own history, but the entire history of the universe. But the impact of these supermassive black holes extends far beyond their immediate surroundings. They play a crucial role in shaping the structure and evolution of entire galaxies over cosmic time. Their immense gravity influences the orbits of stars, the distribution of gas and dust, and even the formation of new stars. Galaxies tend to form in a spiral shape around their supermassive black hole. Think of the black hole as the conductor of an orchestra, orchestrating the movements of billions of stars and the flow of interstellar gas. It guides the galaxy, shaping it, creating harmony. In some cases, these supermassive black holes can even trigger the formation of powerful jets of particles that shoot out into space at near light speed. These jets can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. It's like a cosmic thermostat, regulating the rate of star formation within the galaxy. Furthermore, these galactic nuclei are often associated with active galaxies, some of the most luminous and energetic objects in the universe. Active galaxies, powered by these supermassive black holes, can emit vast amounts of radiation, including radio waves, X-rays, and gamma rays. They can act like cosmic beacons, broadcasting their presence across billions of light years. Active galaxies can tell scientists quite a bit about the conditions that exist in a galaxy and at the center of a black hole. Now, compare these behemoths to their smaller stellar mass cousins. While stellar mass black holes are typically only a few times the mass of our Sun, supermassive black holes can be millions or even billions of times more massive. The difference is so vast that it's almost incomprehensible. It's like comparing a pebble to a mountain or an ant to an elephant. Yet both play their own unique roles in the cosmic ecosystem. Stellar mass black holes are the end products of individual stars, while supermassive black holes are thought to form through more complex processes involving the merging of galaxies, the collapse of massive gas clouds, or the accretion of vast amounts of matter over billions of years. The larger the mass, the more gravity exerted by the object. Stellar mass black holes are usually formed in smaller galaxies. Supermassive black holes are usually found in the center of massive galaxies, like our own Milky Way. The discovery of supermassive black holes has revolutionized our understanding of galaxies and their evolution. It has shown us that these enigmatic objects are not just passive bystanders, but active participants in the cosmic drama, shaping the fate of entire galaxies and influencing the very fabric of spacetime. And their story is far from over. Scientists are still working tirelessly to unravel the mysteries of their formation, their growth, and their impact on the universe around us. What's more, as we learn more about these celestial monsters, we realize there are paradoxes hiding within the very nature of black holes, and the answers could lead to a new era of science. So we've established that black holes are these cosmic vacuum cleaners, relentlessly devouring everything in their path. We've explored their origins, their anatomy, and the mind-bending effects they have on space and time. But what if I told you that everything we thought we knew about black holes was wrong? What if I told you that they're not entirely black after all? Prepare to have your understanding of the universe turned upside down, because we're about to delve into one of the most groundbreaking and perplexing discoveries in the history of astrophysics. It all started with Stephen Hawking, one of the most brilliant minds of our time, a theoretical physicist who dared to challenge the conventional wisdom. Hawking, confined to a wheelchair by a debilitating disease, possessed a mind that could roam freely across the cosmos, unraveling its deepest secrets. In the 1970s, Hawking dropped a bombshell on the scientific community with a revolutionary idea. Black holes aren't truly black. They emit a faint thermal radiation, a ghostly whisper from the edge of oblivion. This radiation, now known as Hawking radiation, arises from quantum effects near the event horizon. But how can something escape from a black hole when nothing, not even light, is supposed to be able to get out? This is where quantum mechanics, the bizarre and often counterintuitive theory of the very small, comes into play. According to quantum mechanics, empty space isn't really empty. It's filled with virtual particles, fleeting pairs of particles and antiparticles that pop into existence and then immediately annihilate each other. Now, imagine this happening near the event horizon of a black hole. One of the virtual particles falls into the black hole while the other escapes. To an outside observer, it appears as if the black hole is emitting a particle. It's as if the black hole is borrowing energy from its own gravitational field to create these particles, and that's precisely what it's doing. Hawking radiation is incredibly faint. The temperature of a black hole emitting Hawking radiation is inversely proportional to its mass. For a black hole with the mass of our Sun, the temperature would be only a few billionths of a degree above absolute zero. So, even though black holes are emitting radiation, they are also absorbing far more energy from the cosmic microwave background, the afterglow of the Big Bang. This means that most black holes are actually growing, not shrinking. However, over immense timescales, longer than the current age of the universe, Hawking radiation will cause black holes to slowly evaporate. They will gradually lose mass, shrink in size, and eventually vanish in a final burst of energy. It's a cosmic slow burn, a process that takes longer than any human lifetime to witness. It will be like the smallest spark from an inferno of a star slowly going out. But Hawking radiation isn't just a theoretical curiosity. It has profound implications for our understanding of black holes, quantum mechanics, and the very nature of reality. And it leads us to one of the most perplexing paradoxes in modern physics, the information loss paradox. Imagine throwing an encyclopedia into a black hole. The encyclopedia contains a vast amount of information, encoded in the arrangement of its letters, words, and sentences. Now, according to classical physics, that information is gone forever. It has been crushed into the singularity, lost beyond the event horizon. But here's the rub. Quantum mechanics tells us that information cannot be destroyed. It must be conserved. This is a fundamental principle of quantum theory, one that underlies our entire understanding of the universe. So, what happens to the information in the encyclopedia? Does it simply vanish from existence, violating one of the most cherished laws of physics? Hawking radiation only carries information about the black hole's mass, charge, and spin. It doesn't seem to contain any information about the objects that fell into it. It's as if the black hole is erasing the past, wiping the slate clean, and emitting only a generic thermal glow. This creates a deep conflict between general relativity, which predicts that information is lost, and quantum mechanics, which insists that it must be conserved. It is as if we are at a cosmic crossroads where two fundamental laws of nature seem to be at odds with each other. This paradox has vexed physicists for decades, leading to intense debates and a flurry of theoretical proposals. Some scientists believe that the information is somehow encoded in the Hawking radiation in a subtle way that we haven't yet understood. Others have suggested that the information is stored on the event horizon itself, like a holographic projection. Still others have proposed radical ideas, such as the existence of firewalls at the event horizon, or the possibility that black holes are not really black at all, but rather fuzzy balls of quantum entanglement. It's a cosmic puzzle with no easy answers. The information loss paradox challenges our most basic assumptions about the universe. It forces us to confront the limits of our knowledge and to question the very nature of space, time, and information. It's a reminder that the universe is far stranger and more mysterious than we can ever imagine. This is not merely an academic debate. This is a battle for the soul of physics, a struggle to reconcile our deepest understanding of the cosmos with the seemingly unbreakable laws of quantum mechanics. And it all starts with the groundbreaking discovery that black holes, those cosmic devourers, aren't quite as black as we once thought. This paradox remains one of the most significant unsolved problems in theoretical physics, a tantalizing enigma that continues to drive scientific innovation and push the boundaries of human knowledge. What if the key to understanding this cosmic conundrum lies in the very fabric of space-time itself? But this clash between general relativity and quantum mechanics, this apparent violation of information conservation, presents us with one of the most profound and perplexing challenges in modern physics. It's a puzzle that has captivated and frustrated the greatest minds in science for decades. The information loss paradox. What happens to the information of everything that falls into a black hole? Is it truly lost forever? Or is it somehow hidden, encoded in a way we don't yet understand? What if, instead of vanishing, all that information is actually stored on the surface of the event horizon itself? It sounds like something straight out of a science fiction film, yet this is the essence of the holographic principle, a mind-bending idea that attempts to resolve the information loss paradox. Imagine a hologram, a three-dimensional image projected from a two-dimensional surface. The holographic principle suggests that the same thing might be true for black holes, and indeed for the entire universe. The idea is that all the information about the inside of a black hole, everything that has ever fallen into it, is encoded on its two-dimensional surface, the event horizon. It's as if the event horizon is a cosmic screen, projecting a three-dimensional reality from a two-dimensional code. This means that the amount of information that a black hole can contain is proportional to the area of its event horizon, not its volume. It's a radical departure from our classical understanding of how information works. If the holographic principle is correct, it would mean that the universe is fundamentally two-dimensional and that our three-dimensional reality is just an illusion. a projection from a distant surface. It's a mind-boggling concept, one that challenges our most basic assumptions about the nature of reality. If the entirety of three-dimensional space is ultimately encoded on a two-dimensional boundary, like information burned onto a compact disk, what does that imply for our understanding of existence? But the holographic principle is not the only attempt to resolve the information loss paradox. There are other, equally intriguing and sometimes controversial ideas on the table. What if the event horizon isn't the smooth, featureless surface that we thought it was? What if it's actually a turbulent, chaotic region, a seething cauldron of quantum activity? This brings us to the firewall theory, a radical proposal that suggests that an infalling observer would encounter a deadly wall of high-energy particles at the event horizon. This firewall would incinerate anything that crosses it, instantly destroying any information that it carries. It's a violent solution to the information loss paradox, one that comes at a steep price. The existence of a firewall would violate Einstein's theory of general relativity, which predicts that an observer should be able to cross the event horizon without experiencing anything particularly unusual. The firewall theory turns the event horizon from a simple boundary in space into a cosmic furnace. Then there are the fuzzball models inspired by string theory, which propose that black holes are not really black at all, but rather fuzzy balls of quantum entanglement. In this view, the event horizon doesn't exist, and the singularity is replaced by a complex, horizonless quantum structure. A fuzzball is not just a different model of a black hole. It suggests that our understanding of space and time is fundamentally flawed. These fuzzballs are not point-like objects, but extended structures, woven from the very fabric of space-time. When something falls into a fuzzball, it doesn't get crushed into a singularity, but rather becomes entangled with the fuzzball's quantum state. The information is not lost, but rather scrambled and redistributed throughout the fuzzball's structure. Each theory offers a different perspective, yet none fully resolves the conflict. So how can we possibly determine which, if any, of these theories is correct? The information loss paradox is more than just an abstract theoretical problem. It has profound implications for our understanding of the universe. Solving it is crucial for developing a unified theory of quantum gravity, a theory that can reconcile general relativity with quantum mechanics. Such a theory would not only explain what happens inside black holes, but also provide a deeper understanding of the nature of space, time, and gravity itself. Think of the information loss paradox as a cosmic Rosetta Stone, a key to unlocking the secrets of the universe. Just as the Rosetta Stone allowed us to decipher ancient Egyptian hieroglyphs, solving the information loss paradox could allow us to decipher the language of the cosmos, to understand the fundamental laws that govern the universe. The search for a solution to the information loss paradox is a quest for a deeper understanding of reality itself. It is a reminder that the universe is full of surprises and that our journey of discovery is far from over. It's a quest that could potentially rewrite the textbooks, reshape our understanding of reality, and unlock secrets we never dreamed possible. And that quest may lead us down a path even more mind-bending than we ever imagined, perhaps to the very possibility that black holes might just be cosmic tunnels through space-time. And so we find ourselves at the precipice of the impossible. We've peered into the abyss, we've wrestled with paradoxes, and we've glimpsed the raw power of black holes. But what if these cosmic destroyers are not just the end of the line? What if they are, in fact, a gateway, a shortcut, a tunnel through the very fabric of space-time itself? It sounds like the stuff of science fiction, and in many ways it is. But hidden within the equations of Einstein's general relativity lies a tantalizing and highly speculative possibility: wormholes. Imagine folding a piece of paper in half. 2 points that were once far apart are now touching. That, in essence, is the idea behind a wormhole, also known as an Einstein-Rosen bridge. A theoretical tunnel connecting two distant points in space-time, potentially allowing for travel across vast cosmic distances in the blink of an eye. Could a black hole be one end of such a tunnel? Could there be another end, perhaps in a completely different galaxy, or even a different universe altogether? The concept of wormholes first emerged from the work of Albert Einstein and his colleague Nathan Rosen in 1935. They were exploring the mathematical solutions to Einstein's field equations when they stumbled upon these bizarre structures. They envisioned them as bridges connecting two regions of space-time, shortcuts through the cosmic tapestry. It was a theoretical curiosity, a mathematical quirk with seemingly no physical reality. It was the stuff of dreams, a plot device used in science fiction stories, but the idea lingered, captivating the imaginations of physicists and writers alike. The prospect of traversing the galaxy in an instant, of bypassing the limitations of the speed of light, was simply too alluring to ignore. But here is where we get to the tricky part, the theoretical part, the part where science slams headfirst into hard reality. Let's say a black hole could theoretically conceal a wormhole. What would that mean for space travel? Could you simply jump into a black hole and emerge somewhere else in the universe? The answer, unfortunately, is probably not, or at least not without some serious, potentially insurmountable obstacles. One of the biggest challenges is stability. Wormholes, as described by general relativity, are inherently unstable. They tend to collapse almost instantly, pinching off the tunnel before anything can pass through. Imagine trying to run through a doorway that is constantly shrinking, closing in on itself. That's the problem with wormholes. To keep a wormhole open, you would need something to counteract the force of gravity, something to hold the tunnel open against its own self-destructive tendencies. And that something, according to current theory, would be exotic matter. This isn't your everyday garden variety matter. Exotic matter has negative mass density, meaning it would have anti-gravity properties, pushing outwards instead of pulling inwards. It's a mind-bending concept, a substance that defies our everyday experience. Does exotic matter exist? Nobody knows for sure. Even if it did exist, could we gather enough of it to stabilize a wormhole? The amount of exotic matter needed would likely be astronomical, perhaps even exceeding the mass of a star. It's a daunting prospect, to say the least. And even if we could overcome these hurdles, there are other dangers to consider. The extreme tidal forces near a black hole, the same forces that cause spaghettification, would still be present, potentially ripping apart anything that dared to venture too close. The radiation levels inside a wormhole, if it indeed exists inside a black hole, would likely be lethal. It's a cosmic gauntlet, a treacherous journey fraught with peril. Now let's separate science fact from science fiction. Wormholes, as portals to other universes or time machines, are firmly in the realm of science fiction. The idea of using them for interstellar travel remains highly speculative, with many theoretical and practical obstacles standing in the way. Consider the energy requirements. Creating or even stabilizing a wormhole would likely require energy levels far beyond our current technological capabilities. We're talking about harnessing the power of stars, or even galaxies. It's also worth noting that the concept of wormholes raises some thorny paradoxes. If you could travel through time using a wormhole, you could potentially alter the past, creating logical inconsistencies and disrupting the very fabric of causality. What if you went back in time and prevented your own birth? Would you still exist? These are the kinds of questions that keep physicists up at night. Despite these challenges, the study of wormholes remains a fascinating area of research. They serve as a theoretical playground, allowing physicists to explore the limits of general relativity and to probe the nature of space, time, and gravity. They push us to think outside the box, to consider possibilities that might otherwise be dismissed. Even if wormholes never become a practical means of transportation, the quest to understand them could lead to profound breakthroughs in our understanding of the universe. What if the true purpose of these Einstein-Rosen bridges isn't transportation, but communication? What if they aren't shortcuts through space, but some bizarre entanglement through dimensions? Are we on the verge of understanding a brand new cosmic postal service? Even if we can't practically traverse them, wormholes inspire the imagination, paving a path to the consideration of alternative universes. But what if I told you that the rabbit hole goes even deeper? That the most mind-bending possibility isn't just that black holes connect to other parts of this universe, but that they could actually create other universes? What if, lurking within the heart of every black hole, lies the seed of a new cosmos? It's a concept that smashes the boundaries of our conventional understanding, a truly cosmological what-if scenario. Forget the Big Bang, forget inflation. What if universes are constantly being born from the singularities within black holes? Imagine a cosmic spawning ground, where new realities are budding off from existing ones, like grapes on a vine. The key lies in challenging the assumption that the collapse of matter into a black hole must inevitably lead to a singularity, that point of infinite density where all known physics breaks down. What if, instead of collapsing into oblivion, the matter undergoes a cosmic bounce? What if at some point the relentless compression reverses, triggering a new phase of expansion? This is the essence of bouncing cosmology, a theoretical framework that proposes that the universe didn't begin with a singularity but rather emerged from a previous phase of contraction. And where better to find such a bounce than within the extreme environment of a black hole? The singularity, then, wouldn't be the end, but a portal, a transition point to a new space-time. In this scenario, the black hole becomes a cosmic womb, nurturing the birth of a new universe within its impenetrable depths. As matter collapses, it reaches a point of maximum density, but instead of being crushed into nothingness, it rebounds, expanding outwards into a new region of space-time. This new region, shielded from our own universe by the event horizon, could then evolve into a completely separate cosmos, with its own laws of physics, its own fundamental constants, and its own unique set of possibilities. Think of it like this. Our universe might be just one of countless others, each born from a black hole in a pre-existing cosmos. It's a multiverse on steroids, an endless chain of creation, with black holes acting as the ultimate cosmic recyclers, taking the remnants of old universes and transforming them into the building blocks of new ones. Does a universe born from the singularity of a black hole have its own black holes? But the speculation doesn't end there. What if, taken to its most extreme conclusion, our own universe originated from a black hole? What if we are living inside the offspring of some gargantuan black hole in a larger parent cosmos? It's a mind-boggling proposition, one that challenges our deepest assumptions about our place in the universe. Imagine a nested hierarchy of universes, each contained within a black hole in a larger universe, like Russian dolls stacked inside each other. Our universe, with its billions of galaxies, its countless stars and planets, might be nothing more than a tiny speck within a much grander cosmic structure. It could mean that the laws of physics we observe, the fundamental constants that govern our reality, are not universal at all, but merely local properties of our particular black hole universe. Perhaps there are other universes out there with different laws of physics, different dimensions, different forms of matter and energy. Universes where gravity is weaker or stronger, where the speed of light is faster or slower, where the very fabric of reality is fundamentally different from our own. These alternate universes, hidden within black holes, could be unimaginably bizarre, beyond our wildest dreams. Now, it's important to emphasize that these ideas are highly speculative, bordering on science fiction. There is no direct evidence to support them, and they remain firmly in the realm of theoretical cosmology. However, they are not simply wild guesses. They are based on extrapolations from our current understanding of physics, on mathematical models that attempt to push the boundaries of our knowledge. The notion that universes could be born from black holes is a tantalizing possibility, one that challenges our fundamental assumptions about the nature of reality. It reminds us that the universe is full of surprises, and that our journey of discovery is far from over. Perhaps, as we continue to probe the mysteries of black holes, we will uncover evidence that supports these mind-bending cosmological models, and perhaps we are not alone. Perhaps there are other universes out there waiting to be discovered, hidden within the hearts of black holes. After all, what have we observed and mapped thus far? A tiny, tiny fraction of the known universe. The quest to understand the cosmos continues. Yet even with these amazing methods of indirect observation, we were still seeing only the effects of black holes, the ripples they create in the cosmic pond. We could infer their presence, measure their mass and spin, and even map their distribution across the universe. But could we ever hope to actually see one? To capture a direct image of these invisible giants? For decades it seemed an impossible dream, a challenge that lay beyond the reach of our technology. Then, in 2019, history was made. A team of international scientists working with a network of telescopes scattered across the globe achieved the seemingly impossible. They captured the first ever direct image of a black hole's shadow. The Event Horizon Telescope, or EHT collaboration, had achieved its goal, mapping the abyss. The image, which quickly went viral, was a triumph of human ingenuity and international collaboration. It showed a bright ring of light surrounding a dark central region. This ring was the superheated gas swirling around the black hole, bent and distorted by its immense gravity. The dark region was the black hole's shadow, the silhouette of the event horizon against the bright background. But how did they do it? How did they manage to image an object that is, by its very nature, invisible? The answer lies in a groundbreaking technique called Very Long Baseline Interferometry, or VLBI. Imagine trying to take a picture of a coin on the surface of the moon using a camera on Earth. The resolution of the camera would need to be incredibly high, far beyond anything currently possible. VLBI overcomes this limitation by linking together multiple telescopes across the globe, effectively creating a single planet-sized observatory. It's like having a giant eye spanning the entire Earth, with a resolution far exceeding that of any individual telescope. The EHT collaboration linked together 8 radio telescopes located in different parts of the world, from Hawaii to Chile, from Spain to the South Pole. By combining the data from these telescopes, they were able to achieve an angular resolution equivalent to being able to read a newspaper in New York from a cafe in Paris. It was an incredible feat of engineering and logistics. The data collected by each telescope was enormous, terabytes upon terabytes of information. It had to be shipped to central processing facilities where it was carefully calibrated and combined. The process was painstaking, requiring years of dedicated effort from hundreds of scientists and engineers. It's like assembling a giant jigsaw puzzle, with each telescope contributing a single piece. Only when all the pieces are in place does the full picture emerge. The first black hole image captured by the EHT was that of M87 star, a supermassive black hole located at the center of the Messier 87 galaxy, some 55 million light-years away. M87 star has a mass equivalent to 6.5 billion suns, making it one of the largest black holes ever discovered. The image revealed a bright ring of light, with a diameter of about 40 billion kilometers. This ring is the emission from the accretion disk around the black hole, superheated gas swirling at nearly the speed of light. But the EHT didn't stop there. In 2022, the collaboration released another groundbreaking image, this time of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A star is much smaller than M87 star, with a mass of only 4 million suns. It's also much closer, only 26,000 light-years away. However, imaging Sagittarius, a star, proved to be even more challenging than imaging M87 star, the gas swirling around Sagittarius. A star is much more turbulent and variable, making it difficult to obtain a stable image. It's like trying to take a picture of a hummingbird in flight. The image of Sagittarius A star revealed a similar ring-like structure to that of M87 star, but with some subtle differences. The ring appears to be slightly tilted and asymmetrical, suggesting that the black hole is spinning. The EHT observations provide stunning confirmation of Einstein's predictions about the behavior of light and matter near black holes. The size and shape of the black hole shadow, the brightness and polarization of the light from the accretion disk, all match the predictions of general relativity with remarkable precision. It's as if Einstein's theory has been put to the ultimate test, and it has passed with flying colors. It would be hard to argue about the legitimacy of black holes after this. The images from the EHT are not just pretty pictures. They are a treasure trove of scientific information, allowing astronomers to study the extreme environment just outside the event horizon in unprecedented detail. They can measure the mass and spin of the black hole, map the magnetic fields in the accretion disk, and even probe the effects of the black hole's gravity on the surrounding spacetime. What's next? Perhaps images of more black holes? Or even more detailed images which lead us to greater discoveries about these celestial giants? These observations are providing valuable insights into the fundamental physics of black holes, helping us to understand the nature of gravity, space, and time itself. But even as we celebrate this monumental achievement, a new window onto the universe has opened, a way to not just see these invisible behemoths, but to hear them. Imagine the cosmos as a vast, silent ocean. For centuries, we've been stranded on the shore, only able to observe the light rippling on the surface. But now we have a new instrument, a cosmic hydrophone that allows us to listen to the deep, rumbling sounds from the depths. We are talking about gravitational waves, ripples in space-time itself, and they are changing everything. What if I told you that the universe has its own symphony? A composition of cataclysmic events that stretch and squeeze space and time? The concept, predicted by Einstein himself over a century ago, remained elusive for decades, almost a philosophical point. Einstein theorized that accelerating massive objects will create ripples in space-time that will travel throughout the universe at the speed of light. It was almost as if the cosmos itself was a giant drum, vibrating with the echoes of creation and destruction. Think of it like dropping a pebble into a still pond. The pebble creates ripples that spread outwards, disturbing the water. Now imagine dropping something much larger, like a boulder, or even two boulders colliding. The ripples would be much larger, more powerful, and they would travel much further. Black hole collisions create the largest ripples of all. It wasn't until 2015, 100 years after Einstein published his theory, that scientists were able to directly detect these gravitational waves. This monumental achievement was made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a pair of giant detectors located in Livingston, Louisiana and Hanford, Washington. Think of LIGO as two incredibly sensitive ears listening for the faintest whispers from the cosmos. Each detector consists of two arms 4 kilometers in length, arranged in an L shape. Lasers are beamed down these arms and bounced off mirrors, creating an interference pattern. When a gravitational wave passes through, it stretches and squeezes the arms ever so slightly, altering the interference pattern. The amount of stretching and squeezing is incredibly small, smaller than the width of a proton. It is an incredible testament to engineering, with machinery so precise that it can measure a change in space smaller than an atom. The first gravitational wave signal detected by LIGO came from the merger of two black holes, each roughly 30 times the mass of our Sun, located 1.3 billion light-years away. The signal, lasting only a fraction of a second, was a faint chirp, a cosmic crescendo as the two black holes spiraled inwards, collided, and merged into a single, larger black hole. The amount of energy released in this collision was staggering, equivalent to several times the mass of our Sun being converted into gravitational waves. Imagine two cosmic Goliaths crashing together, shaking the fabric of space-time itself. That signal, named GW 150914, marked the dawn of a new era in astronomy. We had finally opened our ears to the gravitational wave universe. Since that first detection, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave signals, most of them from the mergers of black holes. Each detection provides a unique glimpse into the lives and deaths of these enigmatic objects. Think of gravitational waves as a cosmic Morse code, each signal telling a story about the events that created it. What exactly do these signals tell us? By analyzing the frequency and amplitude of the gravitational waves, scientists can precisely measure the masses and spins of the merging black holes. This allows them to test Einstein's theory of general relativity in the most extreme environment imaginable. It's like putting Einstein's ideas through a cosmic obstacle course, pushing them to the very limits of their validity. Moreover, these collisions reveal a great deal about the black hole population and their behavior. Scientists can learn what are the masses of black holes. How are they distributed in the cosmos? How frequently do they merge? Are smaller or larger black holes merging more often? It's like conducting a census of the black holes in the universe, learning about their demographics, their habits, and their relationships. The gravitational waves act like a cosmic time machine, allowing us to study events that happened billions of years ago when the universe was much younger. The black hole collision detected by LIGO 150914 occurred 1.3 billion years ago, long before dinosaurs roamed the Earth. By studying these ancient signals, we can learn about the conditions that existed in the early universe. Imagine listening to a fossil, a sonic echo of events from a distant past. Gravitational waves are not just limited to black hole mergers. They can also be produced by other cataclysmic events, such as the collision of neutron stars, the explosion of supernovae, and even the Big Bang itself. Scientists hope to eventually detect gravitational waves from these sources, providing even more insights into the workings of the universe. What could we see with better ears? Imagine a universe painted not with visible light, but with the very bending of space-time itself. From what we've learned thus far, angular momentum can have profound effects on black holes, which opens a new door in our investigation of them. Gravitational waves have opened our ears to a universe of cataclysmic sounds, whispers from the most violent events imaginable. But what if those sounds, those faint chirps and roars, are also telling us something about the very nature of the black holes themselves? What if they're not all the same? We've talked about mass, we've touched on charge, but there's another crucial property that can dramatically alter a black hole's behavior and even hint at what might lie hidden within. I'm talking about spin. Imagine a figure skater pulling their arms in tight as they spin, rotating faster and faster. That's essentially what happens when a massive star collapses to form a black hole. The star's original rotation, its angular momentum, is conserved, concentrated into an incredibly small space. This doesn't just create a smaller black hole. It creates an entirely different kind of black hole. Up until now, we have been primarily discussing a Schwarzschild black hole, a non-rotating black hole. Named after Karl Schwarzschild, the first person to find a solution to Einstein's field equations that described a black hole. It is the simplest kind of black hole. It has mass, but no electric charge and no angular momentum. Now let's dive into a world even more warped and wonderful. A rotating black hole, also known as a Kerr black hole, named after mathematician Roy Kerr, who discovered this solution to Einstein's equations. It possesses mass, but more importantly, it also has angular momentum. It spins. This spin fundamentally changes the black hole's structure. The event horizon, that point of no return, is still there, but it's no longer the only defining feature. Rotating black holes possess another, even stranger region outside the event horizon, the ergosphere. The what? Ergosphere. This isn't some impenetrable wall, but a region of space-time that is being dragged around by the black hole's rotation. Picture this. You're standing just outside the event horizon of a non-rotating black hole. You can resist its pull, fire up your rockets and escape. But try doing that outside a Kerr black hole within the ergosphere, and you will find it impossible to remain stationary. Space-time itself is being dragged around you like a swirling vortex, forcing you to co-rotate with the black hole. It's as if you're caught in a cosmic whirlpool. You might ask, why is this important? Well, the ergosphere isn't just a weird curiosity. It holds a secret, a potentially mind-blowing possibility. Could we somehow extract energy from a spinning black hole? The answer, according to theory, is yes. This idea brings us to the Penrose process, a theoretical method proposed by physicist Roger Penrose in 1969. Here's the gist. Imagine you enter the ergosphere and release an object. You will need to fire it backwards to you as you enter the ergosphere to slow you down. The object falls into the black hole, but is now traveling against the spin. You, on the other hand, are flung outwards, escaping the ergosphere with more energy than you had when you entered. The black hole's rotation has slowed slightly, but you've gained energy in the process. Think of it as skimming off the energy of the black hole's spin without actually falling in. It sounds like something out of a science fiction novel, a cosmic power plant fueled by the rotation of a black hole. While it's unlikely we'll be building black hole power stations anytime soon, the Penrose process highlights the immense energy locked within these spinning behemoths. It is important to keep in mind that even though the Penrose process is theoretically possible, it is not clear whether there is any way to actually implement it in practice. But regardless, the Penrose process tells us something deep about the nature of the black hole. The faster a black hole spins, the larger its ergosphere and the more energy that can be extracted. The Penrose process isn't the only method to extract energy from a black hole. A similar process can occur via magnetic fields, called the Blandford-Znaiec process. Both of these processes tell us that black holes are not just cosmic vacuum cleaners, but also cosmic engines capable of generating tremendous amounts of power. But what does spin tell us about what lies inside the black hole? Does rotation change the nature of the singularity itself? The answer, once again, is a resounding yes. In a non-rotating black hole, the singularity is thought to be a point, an infinitely small volume of infinite density. But in a rotating black hole, the singularity is stretched out into a ring. Yes, you heard that right, a ringularity. What exactly does that mean? Well, for one thing, it changes the way we think about the black hole's interior. Is it possible to pass through the ringularity, avoiding the infinite density and entering some other region of space-time? It's a question that continues to fuel theoretical research, blurring the line between science fact and science fiction. The ringularity makes the interior of the black hole more traversable. As long as you can avoid the ringularity itself, you may be able to avoid being spaghettified. What does this mean? The math shows some very strange and counterintuitive effects, such as being repelled rather than attracted. Spin adds another layer of complexity, another twist in the already warped reality of black holes. It is a crucial ingredient in understanding their behavior, their energy output, and even their potential connection to other universes. As we continue to probe the secrets of these spinning monsters, we are pushing the boundaries of our knowledge and challenging our most fundamental assumptions about the cosmos. And there could still be another kind of black hole out there, ones that were not formed from dying stars, but existed since the beginning of time. And there could still be another kind of black hole out there, ones that were not formed from dying stars, but existed since the beginning of time. What if the universe's most efficient garbage disposals weren't all born from stellar demise? What if some of them are ancient relics, cosmic fossils from the universe's infancy? Imagine a black hole, not forged in the heart of a dying star, but spontaneously erupting from the primordial soup of the early cosmos. These hypothetical objects are known as primordial black holes, and their existence, though unproven, could revolutionize our understanding of the universe. Think back to the first moments after the Big Bang. The universe was a seething cauldron of energy and matter, far denser and more chaotic than anything we can imagine today. In this extreme environment, fluctuations in density could have created pockets of space so incredibly compressed that they collapsed directly into black holes, bypassing the need for a star altogether. Imagine a cosmic pressure cooker, where space itself is being squeezed to the breaking point. Now here is where things get interesting. Unlike stellar black holes, which have a limited range of masses depending on the size of their progenitor stars, primordial black holes could theoretically span an enormous range of sizes, from microscopic quantum objects smaller than an atom to intermediate mass black holes weighing in at hundreds or even thousands of solar masses. We could be talking about black holes so minuscule they make subatomic particles look like celestial bodies. What implications would that have? These primordial black holes could have formed with any mass whatsoever. Some scientists theorize that primordial black holes could explain the existence of dark matter, the mysterious substance that makes up most of the matter in the universe but does not interact with light. What if these black holes are the missing link? If they are indeed dark matter, we are surrounded by billions or even trillions of these primordial black holes. Imagine the implications. They would be everywhere, silently influencing the orbits of stars and galaxies. They would be like cosmic ghosts, present but unseen, their gravity shaping the universe from behind the scenes. It is speculated that small primordial black holes have a minimum mass equal to 100 millionth of a gram. This equals the mass of a large virus or an amoeba. Such a black hole would be approximately 0.000000001 millimeters across. And what if some of these primordial black holes managed to survive to the present day, scattered throughout the universe like ancient cosmic fossils? Could they provide the seeds for the supermassive black holes that lurk at the centers of galaxies? Instead of stellar mergers, massive gas clouds, or direct collapses, what if the supermassive black holes began as primordial black holes? The idea is that a primordial black hole may have served as a gravitational anchor for larger galaxies to accumulate around. These black holes would have acted as the original mass around which galaxies would have developed. Detecting these primordial relics, however, is an immense challenge, because these primordial black holes are too small to detect. Using the methods astronomers use to observe stellar black holes, scientists have had to come up with new methods for observing these cosmic fossils. If some survived until today, how could we find them? One intriguing possibility lies in gravitational lensing, a phenomenon where the gravity of a massive object bends and magnifies the light from a more distant object behind it. If a primordial black hole were to pass in front of a star, it could act like a cosmic magnifying glass, briefly brightening the star's light. It is a cosmic spotlight, suddenly shining on a long-lost relic of the early universe. Another possibility involves searching for the faint gamma-ray bursts that might be emitted by the smallest primordial black holes as they evaporate via Hawking radiation. These miniature black holes would be slowly leaking energy until eventually they would pop out of existence. It would be a long wait for them to pop out of existence. Imagine witnessing the final breath of a cosmic relic, a fleeting moment of brilliance as it vanishes from the universe. There is even the possibility of searching for the gravitational waves emitted by primordial black holes as they merge with each other. These mergers would create distinctive signals, different from those produced by stellar black holes, offering a unique fingerprint of their primordial origin. The potential discovery of such a merger would provide a monumental discovery about the state of the early universe. The search for primordial black holes is a long shot, a cosmic gamble. But the potential payoff is enormous. Finding even a single one of these ancient relics would provide a window into the universe's earliest moments, shedding light on the conditions that existed just after the Big Bang and potentially solving the mystery of dark matter. It would be like discovering a missing piece of the cosmic puzzle, a key to unlocking the secrets of our origins. But as tantalizing as these glimpses into the hearts of black holes are, as groundbreaking as these new tools are, they all point towards a deeper, more fundamental problem. A chasm in our understanding so profound that it threatens to swallow our entire picture of the universe. We have two magnificent theories, pillars of modern physics, each incredibly successful in its own domain. On one hand, we have Einstein's general relativity, a beautiful, elegant description of gravity and the large-scale structure of the cosmos. On the other hand, we have quantum mechanics, a bizarre, counterintuitive, but incredibly accurate theory of the very small, the world of atoms and subatomic particles. The only problem? They don't play well together. In fact, they actively fight each other, leading to paradoxes and contradictions that have baffled physicists for decades. Black holes, with their extreme gravity and quantum weirdness, are ground zero for this conflict. It is in these cosmic laboratories that the incompatibility of our two most successful theories becomes glaringly obvious. Where general relativity predicts smooth, continuous space-time, quantum mechanics insists on a grainy, probabilistic reality. Where general relativity describes gravity as a force, quantum mechanics describes it as an exchange of particles. How can we reconcile these two fundamentally different views of the universe? This is the central question driving modern theoretical physics. The singularity, that infinitely dense point at the heart of every black hole, is the ultimate battleground. General relativity predicts its existence, but also predicts its own demise at this point. The equations simply break down, spitting out infinities and nonsensical results. It's as if the universe is telling us, you haven't figured this out yet, your theories are incomplete. And quantum mechanics, it has nothing to say about the singularity. It simply can't handle the extreme gravity and space-time curvature that exist in this region. It is like trying to use a map of a city to navigate the ocean. The event horizon, that invisible boundary beyond which nothing can escape, is another source of conflict. General relativity describes it as a smooth, featureless surface, a one-way membrane. But quantum mechanics suggests that it might be a seething cauldron of quantum activity, a place where virtual particles pop in and out of existence, where information is scrambled and potentially lost. It's as if we are looking at the same object through two different lenses, each revealing a completely different picture. So, what is the solution? What is the missing piece of the puzzle? Most physicists believe that we need a new theory, a theory that can seamlessly blend general relativity and quantum mechanics into a single, unified framework. This is the holy grail of modern physics, the theory of everything. But how do we get there? There are two leading contenders, two promising approaches that are pushing the boundaries of our understanding: string theory and loop quantum gravity. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings, far smaller than an atom, vibrate at different frequencies, giving rise to the different particles and forces that we observe. It's like a cosmic symphony, where each note, each particle is produced by a vibrating string, and gravity, according to string theory, is just another vibration, another note in the symphony. Loop quantum gravity, on the other hand, takes a different approach. It quantizes space-time itself, breaking it down into tiny, discrete chunks like pixels on a screen. These chunks of space-time are linked together in a network of loops, creating a fundamentally granular structure. Imagine the fabric of space-time not as a smooth sheet, but as a chainmail woven from countless tiny loops. Both string theory and loop quantum gravity offer tantalizing glimpses of a unified theory, but both also face significant challenges. String theory requires extra dimensions of spacetime, dimensions that we have yet to detect. Loop quantum gravity struggles to reproduce the smooth spacetime predicted by general relativity at large scales. It is like trying to build a puzzle with pieces that don't quite fit. forcing us to question our assumptions and to look for new ways to connect the dots. But despite these challenges, the quest for a theory of quantum gravity continues, driven by the desire to understand the universe at its deepest level. It is a quest that requires not only mathematical brilliance, but also creative thinking and a willingness to challenge the conventional wisdom. Think of it as a cosmic treasure hunt, where the prize is nothing less than a complete understanding of reality. Solving this conflict between general relativity and quantum mechanics is not just an academic exercise. It has profound implications for our understanding of black holes, the early universe, and the very nature of space and time. Perhaps the singularity is not a point at all, but some other exotic structure predicted by a quantum theory of gravity. Perhaps the event horizon is not a one-way membrane, but a complex dynamic region where information is somehow preserved. These are the questions that are driving the next generation of theoretical physicists. It's perhaps the greatest challenge facing modern theoretical physics. But are we doomed to never know the full story of what plunges into these cosmic maws? Are all the unique characteristics of matter, the intricate details of entire worlds, simply wiped clean from existence? This brings us to one of the most elegant and yet most puzzling concepts in black hole physics, the no-hair theorem. Imagine a cosmic barber, meticulously shaving away all the distinguishing features of anything that falls into a black hole. Sounds absurd, doesn't it? Yet, in essence, that's what the no-hair theorem suggests. It postulates that once a black hole has settled down, it is defined by only three properties: its mass, its electric charge, and its angular momentum, or spin. That's it. Everything else, all the messy details of what went in, is seemingly lost forever. Think about it. A star composed of hydrogen, a planet made of iron, a rogue collection of space dust. According to this theorem, once they cross the event horizon, their individual identities are irrelevant. The black hole remembers only how much mass, charge, and spin it has gained. It's as if they've all been homogenized into a single bland cosmic smoothie. This concept is named the no-hair theorem because physicists like to use the term hair to describe all the other complex properties that an object can have. A human, for example, has a great deal of hair. Height, weight, shoe size, hair color, and the amount of wrinkles are all physical ways of describing a human. Similarly, any object has many different parameters to describe the way it is. The no-hair theorem says all of these things disappear once that object enters the black hole. The black hole is bald, it has no hair. Why does this happen? Why are black holes so seemingly forgetful? The answer lies in the extreme nature of gravity. The intense gravity of a black hole crushes all matter into the singularity, obliterating its previous structure. Any external field, such as a magnetic field or a gravitational quadrupole moment, quickly dissipates as the black hole settles into a stationary state. It's as if gravity is performing a cosmic lobotomy, erasing the memory of the black hole's past. The no-hair theorem has profound implications. It suggests that black holes are incredibly simple objects defined by just a handful of numbers. They are the ultimate example of cosmic simplicity emerging from extreme complexity. But it also raises some troubling questions, particularly in light of the information loss paradox we discussed earlier. If all the information about what falls into a black hole is truly lost, does that violate the fundamental laws of quantum mechanics? This puzzle has occupied physicists for decades, leading to all sorts of wild and speculative ideas. Is the information somehow encoded on the event horizon, as suggested by the holographic principle? Is it hidden in the Hawking radiation, waiting to be deciphered? Or is there something fundamentally wrong with the no-hair theorem itself? Perhaps in the extreme quantum environment around a black hole, some hair can actually persist, subtly altering its properties in ways we haven't yet understood. Consider this. The no-hair theorem is based on classical general relativity, which, as we know, breaks down at the singularity. What if a theory of quantum gravity, a theory that successfully combines general relativity with quantum mechanics, reveals new physics that allows for some information to escape? Imagine a tiny loophole, a quantum crack in the armor of the event horizon, allowing a whisper of the past to leak out. Some physicists have proposed that quantum gravity effects could create tiny wrinkles or imperfections on the event horizon, deviations from the perfect smoothness predicted by classical theory. These wrinkles, this quantum hair, could potentially encode information about the black hole's history. It would be like finding a faint fingerprint on an otherwise pristine surface, a subtle clue to a long-forgotten crime. Others have suggested that the internal structure of a black hole might be far more complex than we currently imagine, with exotic states of matter, or even entirely new forms of space-time. Perhaps these hidden structures can retain some memory of the objects that fell in, preserving information in a way that is invisible to our current observations. It's akin to a house with a seemingly minimalist exterior, actually hiding a labyrinth of elaborately decorated rooms within. The question of whether black holes truly have no hair remains one of the most fascinating and challenging problems in modern physics. It's a question that probes the very limits of our knowledge and forces us to confront the fundamental nature of information, gravity, and the universe itself. As we continue to explore these enigmatic objects, we may find that the no-hair theorem is not the final word, but just another stepping stone on our journey to a deeper understanding of the cosmos. Will we find some rogue strands of hair clinging to these cosmic barbershops? Or are black holes truly the ultimate erasers of history? But now we've arrived at a rather unnerving fork in the road. Have we truly understood the event horizon, that seemingly smooth and serene boundary that dictates what can and cannot escape a black hole? Or is there something far more bizarre lurking just beyond our grasp? We've treated the event horizon as this nice, neat surface, a one-way ticket into the abyss. But what if that picture is fundamentally wrong? What if that classical smoothness is an illusion, and the reality is far more jarring than we ever imagined? Imagine falling into a black hole expecting a gentle transition, a seamless journey into the unknown. What if instead you slammed headfirst into a wall of fire? This, in essence, is the firewall paradox, a mind-bending proposal that challenges our most basic assumptions about the event horizon. Is there a possibility that infalling observers might encounter a deadly wall of high-energy particles due to quantum effects? According to this theory, the event horizon isn't the smooth, continuous surface we thought it was. It's a roaring inferno, a cosmic furnace that would incinerate anything that dares to cross its path. Where did this crazy idea come from? It stems from the ongoing battle between general relativity and quantum mechanics, specifically the information loss paradox. Remember how quantum mechanics insists that information cannot be destroyed? If that's true, then what happens to all the information about the objects that fall into a black hole? Does it simply vanish, violating a fundamental law of physics? The firewall theory offers a rather brutal solution to this paradox. It suggests that the event horizon is not empty space, but a region of extremely high-energy particles created by the entanglement of outgoing Hawking radiation with incoming particles. This entanglement creates a discontinuity in space-time, a sharp boundary that would act like a brick wall for any infalling object. Think of it as hitting a concrete wall after believing for years you are about to jump in a pool. This firewall would instantly destroy any information carried by the infalling object, resolving the information loss paradox in a rather violent manner. However, the existence of a firewall would violate a key principle of general relativity, the equivalence principle. This principle states that an observer in freefall should not experience anything unusual as they cross the event horizon. It should be a smooth and uneventful transition. So, the firewall paradox puts us in a bind. Either we violate quantum mechanics and lose information, or we violate general relativity and encounter a fiery death. Is there an alternative? Can we somehow reconcile the demands of both general relativity and quantum mechanics without resorting to cosmic immolation? This brings us to another intriguing proposal, one inspired by string theory, the fuzzball. What if the black hole interior isn't empty space, but a complex, horizonless quantum structure? Imagine replacing the event horizon with a fuzzy, ill-defined boundary, a region where spacetime is no longer smooth and continuous, but rather a tangled mess of quantum strings. This is the essence of the fuzzball conjecture. According to this idea, a black hole is not a point like Singularity surrounded by empty space. It's a giant, messy ball of strings, vibrating and interacting in countless ways. These strings, the fundamental building blocks of the universe according to string theory, are not confined to a single point. They are spread out over a region of space, creating a fuzzy, ill-defined boundary. When something falls into a fuzzball, it doesn't encounter a sharp firewall. Instead, it gradually becomes entangled with the fuzzball's strings, its information scrambled and redistributed throughout the structure. Think of it as falling into a giant ball of yarn, becoming tangled and interwoven with the threads, your individual identity lost in the chaotic mess. In this scenario, information is not destroyed, but rather scrambled and preserved in the complex quantum state of the fuzzball. The fuzzball offers a gentler, more quantum mechanical picture of the black hole, one that avoids the violent implications of the firewall theory. However, it also requires us to abandon our classical notions of spacetime and to embrace the bizarre and counterintuitive world of quantum entanglement. Does this mean our current understanding of black holes is flawed? Are we missing a crucial piece of the puzzle? Could there be more to the event horizon than meets the eye? Are firewalls real? Are black holes really fuzzballs? Or is the truth somehow even stranger, more unexpected than we can currently imagine? What is the true nature of the black hole boundary? The answer to these questions remains elusive, but the debate rages on, pushing the boundaries of our knowledge and challenging our most fundamental assumptions about the universe. It would seem like we are not any closer to a consensus, but perhaps a new generation of scientists can carry the torch and take us to the finish line. We've journeyed to the very edge of what we know, peering into the abyss and wrestling with paradoxes that threaten to unravel our understanding of the universe. The firewall or the fuzzball, which is it? How can we solve this puzzle? But what if the answer lies not in observing these objects but constructing them ourselves, at least virtually? For centuries, science has progressed through observation and experimentation. But when direct experimentation is impossible, when the object of study is hidden behind an impenetrable barrier, what do? You build a model, a simulation, a virtual laboratory where you can test your ideas and explore the consequences of your theories. And that is where the remarkable power of supercomputers comes into play. Imagine trying to understand the weather without ever stepping outside. You could measure the temperature, the wind speed, the humidity. But to truly predict what will happen, you need to create a computer model of the atmosphere, a virtual world where you can simulate the complex interactions of air, water, and energy. That is also true for black holes. Black holes are impossible to reach, but we can use the world's most powerful technology to create a black hole on our own. That's precisely what scientists are doing with black holes. They are using the world's most powerful supercomputers to create virtual black holes, simulations that allow them to explore the extreme physics of these objects in unprecedented detail. These are not just pretty pictures. These are sophisticated numerical experiments, mathematical models that test Einstein's theories in the most extreme regimes imaginable. But why resort to simulations? Why not just rely on the mathematics? Because the equations of general relativity, while elegant, are also incredibly complex. For simple scenarios, like the orbit of a planet around a star, they can be solved analytically, meaning you can find an exact mathematical solution. But for more complex situations like the merger of two black holes, the equations become intractable, impossible to solve with pencil and paper. That's where supercomputers enter the stage. These massive machines, capable of performing trillions of calculations per second, can churn through the equations of general relativity, approximating solutions that would be impossible to obtain by any other means. These simulations are so complex they require computers the size of a small building. But it's more than just brute force computation. The simulations are based on sophisticated algorithms, clever mathematical techniques that allow scientists to capture the essential physics of black holes without getting bogged down in unnecessary details. It's like creating a simplified version of reality, a virtual world that captures the key features of the real thing. What do these simulations allow us to see? They can show us the formation of black holes, the dramatic collapse of massive stars as gravity overwhelms all other forces. It is a cosmic ballet of immense energy, the very creation of these dark beings, visualized for our eyes. These simulations also allow us to witness the chaotic dance of matter in accretion disks, the swirling maelstrom of gas and dust that surrounds many black holes. We can see how the matter is heated to millions of degrees, how it emits intense radiation, and how it is ultimately swallowed by the black hole. We can observe the mergers of black holes, the cataclysmic collisions that send ripples of gravitational waves across the cosmos. We can track the distortions of spacetime as the black holes spiral inwards, collide and merge into a single larger black hole. It is like watching a slow-motion explosion, a cosmic car crash that unfolds over millions of years. These visualizations give us a unique window into the otherwise inaccessible processes. It's as if we are peering behind the curtain of the universe, witnessing events that would be invisible to our eyes. But the ultimate goal is to computationally probe the conditions inside black holes, to venture beyond the event horizon and explore the nature of the singularity. This is the most challenging aspect of black hole simulations, pushing the limits of our computational abilities and our theoretical understanding. Can these simulations help us solve the information loss paradox? Can they shed light on the nature of quantum gravity? The simulations strive to computationally probe the conditions inside. Can they reveal the existence of firewalls or fuzzballs or some other exotic structure that we have yet to imagine? While these simulations cannot directly replicate the quantum weirdness that is thought to exist near the singularity, they can provide valuable clues, hints that can guide our theoretical investigations. The supercomputers act as a bridge, connecting our theoretical ideas with the real world, allowing us to test our assumptions and to explore the consequences of our theories. If our knowledge of black holes is a vast puzzle, then computer simulations provide countless extra pieces to help us understand this complicated area of science. These are tools that allow us to boldly go where no human can physically venture, into the very heart of a black hole, expanding our view and our understanding. As these models increase in sophistication, what new features of these powerful entities will be revealed? Perhaps the answer is closer than we realize. So we've journeyed to the very edge of what we know, peering into the abyss and wrestling with paradoxes that threaten to unravel our understanding of the universe. The firewall or the fuzzball? Which is it? How can we solve this puzzle? But what if the answer lies not in observing these objects but constructing them ourselves, at least virtually? What mysteries can powerful supercomputers unlock? As simulations of black holes become more and more sophisticated, are we learning everything that we can? Perhaps not. Perhaps we have been looking at the effects of black holes all wrong. Rather than focusing on what goes in, what if we looked at what comes out? Consider the most powerful objects in the universe, quasars. These beacons of light, visible across billions of light years, are powered by supermassive black holes at the centers of galaxies. But what are we actually seeing when we observe a quasar? We see an intensely bright point of light, a lighthouse in the cosmic dark. But this light is not coming directly from the black hole itself. It's coming from the accretion disk, the swirling whirlpool of gas and dust that surrounds the black hole. But there is another, even more spectacular phenomenon associated with many quasars and other active galaxies. Colossal jets of plasma, ejected at near light speed from the vicinity of the black hole. Imagine a cosmic fire hose, blasting matter out into space at speeds approaching the ultimate speed limit. These jets, often extending for millions of light years, are some of the most energetic and awe-inspiring displays in the universe. Why are they so powerful? What is the mechanism that launches and focuses these jets? And what role do they play in the evolution of galaxies? The answer, as with so much in the realm of black holes, is complex and not fully understood. But the leading theories point to the interplay of gravity, magnetic fields, and the spin of the black hole itself. Think of the accretion disk as a cosmic dynamo, a machine that converts gravitational energy into magnetic energy. As matter spirals inwards, it becomes superheated and ionized, creating a plasma of charged particles. These charged particles swirling around the black hole generate powerful magnetic fields. It's like winding up the giant rubber band, storing energy that can be released in a sudden burst. These magnetic fields, twisted and tangled by the black hole's spin, can then act like a cosmic catapult, launching particles outwards along the black hole's axis of rotation. It's as if the very fabric of space-time is being used to create a cannon. The black hole acts like a giant engine, converting gravitational potential energy into kinetic energy. Think of it like water flowing down a dam to power turbines. The infalling material is the water, and the magnetic fields are the turbines. The outflowing jet is a byproduct of this powerful process. But what are these jets actually made of? The jets are primarily composed of plasma, a superheated state of matter where electrons have been stripped from their atoms. This plasma is incredibly tenuous, far less dense than the air we breathe. But because it's moving at near light speed, it carries an enormous amount of kinetic energy. It's like a bullet being shot out of a high-powered rifle. The plasma in the jets interacts with the surrounding intergalactic medium, the sparse gas and dust that permeates the space between galaxies. This interaction can create shock waves, regions of compressed and heated gas that emit intense radiation across the electromagnetic spectrum. It's as if a car crashed at high speed, and you could see the shock wave coming off of the wreck. These jets are not just passive bystanders. They have a profound impact on their host galaxies, regulating star formation and distributing heavy elements. The jets can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. It's like a cosmic thermostat, controlling the temperature of the galaxy. If the black hole is too active, it can stifle star formation, turning the galaxy into a red and dead environment. On the other hand, if the black hole is too quiescent, the galaxy can become overpopulated with stars, leading to overcrowding and instability. What is the perfect balance between too much star formation and not enough star formation? It's a question astronomers are still trying to answer. The jets can also transport heavy elements, created in the cores of stars, out into the intergalactic medium. This process enriches the surrounding space with the building blocks of new stars and planets. It's as if the black hole is fertilizing the galaxy, spreading the seeds of future generations. These elements can eventually form new stars, planets, and even life. It is a powerful engine of change, shaping the destiny of galaxies over billions of years. Think of it as a way in which galaxies can balance and grow. These spectacular external displays are all connected to the powerful engine hidden within the black hole. The jets are a visible manifestation of the black hole's immense gravity, its swirling accretion disk, and its twisted magnetic fields. They are a reminder that black holes are not just cosmic vacuum cleaners, but also cosmic power plants, capable of generating tremendous amounts of energy and influencing the evolution of entire galaxies. Is there a limit to the power of these jets? Can they eventually disrupt or even destroy their host galaxies? These are questions that continue to drive research into the hearts of darkness. So the next time you gaze up at the night sky, remember that there is more than meets the eye. Behind the serene beauty of the galaxies lurks the power of supermassive black holes. their jets shaping the cosmos in ways we are only beginning to understand. But if that is all there is to learn about black holes and their galaxy-shaping jets, consider this. What if some of these jets, under the correct circumstances, actually cause star formation? Can jets push away enough of the surrounding gas and dust that areas are formed that are perfect for creating new stars? There's still so much to explore about the mechanics of these amazing cosmic behemoths. Yet, as we grapple with the power of these galactic fountains, shooting plasma across unimaginable distances, a question arises. Are we truly capturing the complete picture of these enigmatic objects? Perhaps there's a hidden layer of complexity, a theoretical twist that could reshape our understanding of black holes once again. What if these cosmic behemoths could possess something akin to an electric charge? It sounds like a departure from reality, but it leads us to a fascinating exploration of theoretical possibilities. Imagine a black hole not just with mass and spin, but also carrying an electrical charge. Could such a bizarre entity even exist? The answer lies within the equations of general relativity, specifically in a solution known as the Reissner-Nordström black hole. This solution, named after the physicists Hans Reissner and Gunnar Nordström, describes a black hole that possesses both mass and electric charge, adding another layer of complexity to the already warped spacetime surrounding these objects. But how does charge influence the nature of a black hole? Prepare for another mind-bending concept. A charged black hole exhibits an additional complexity, the possibility of multiple event horizons. Instead of a single inescapable boundary, a Reissner-Nordström black hole can possess an inner and an outer event horizon, separated by a region of space where the gravitational and electromagnetic forces are in a delicate balance. Think of it as a series of cosmic shields, protecting the singularity at the black hole's heart. But there's more. The presence of charge also alters the nature of the singularity itself. In a non-charged black hole, the singularity is thought to be a single point, an infinitely dense region where space-time ceases to exist. But in a charged black hole, the singularity can take on a different form, potentially becoming a ring or even a wormhole, a theoretical tunnel through space-time. It sounds like science fiction, doesn't it? But these are some of the mathematical consequences of adding charge to the mix. However, before we get carried away with dreams of traveling through charged black holes, let's pause and consider a crucial point. While these charged black holes are mathematically possible, they are likely extremely rare, perhaps even non-existent in the real universe. Why? Because astrophysical black holes, those formed from the collapse of stars or the accretion of gas, are expected to quickly neutralize their charge. Imagine a black hole formed from the collapse of a massive star. The star is composed of protons, which are positively charged, and electrons, which are negatively charged. The same is true of clouds of gas. But stars and gas clouds have nearly equal numbers of protons and electrons, and therefore are almost electrically neutral. The black holes that these clouds form are thus also electrically neutral. So what happens if they become positively or negatively charged? If a black hole starts to accumulate a net electric charge, it will quickly attract oppositely charged particles from the surrounding space. Electrons will be drawn towards a positively charged black hole, and protons will be drawn towards a negatively charged black hole. This process, known as charge neutralization, will rapidly reduce the black hole's net charge, restoring it to a neutral state. It's like a cosmic balancing act, where the universe seeks to eliminate any imbalances in electric charge. This means that most of the black holes we observe in the universe, those lurking at the centers of galaxies or orbiting companion stars, are likely very close to being electrically neutral. Any initial charge they might have possessed would have been quickly dissipated by the influx of oppositely charged particles. These black holes would thus be Schwarzschild black holes, which, as we remember, have mass but no electric charge and no angular momentum, or Kerr black holes, which have mass and angular momentum or spin. Reissner-Nordstrom black holes with mass and charge may be extremely rare in nature. So, why bother studying these theoretical curiosities? Why spend time and effort exploring objects that are unlikely to exist in the real world? The answer is that these charged black holes, like all theoretical constructs, provide valuable insights into the fundamental nature of gravity, spacetime, and the laws of physics. They allow us to test our theories in extreme conditions, to explore the boundaries of what is possible, and to gain a deeper understanding of the universe. Think of these charged black holes as mathematical playgrounds, where we can experiment with different parameters and explore the consequences of our assumptions. They help us to refine our models, to identify potential flaws in our theories, and to develop new ideas about the nature of reality. Moreover, the study of charged black holes can have unexpected applications in other areas of physics. The mathematical techniques developed to analyze these objects can be used to study other charged systems, such as charged particles in strong electromagnetic fields. It is as if studying charged black holes helps us see connections to the rest of the universe. So while astrophysical black holes may be electrically neutral, the theoretical possibility of charged black holes allows scientists to explore the nature of gravity, to refine our theoretical models, and to potentially uncover new physics that applies to a wide range of phenomena. What began as a theoretical curiosity has opened new and unexpected avenues of investigation. And what other bizarre theoretical possibilities exist in the realm of these cosmic behemoths? But even as we contemplate the theoretical limits of charged black holes, entities that may barely exist in our universe, the human mind, forever restless, continues its relentless exploration of what is possible. It is human nature to ponder what could exist, and what strange properties it may contain. We can not only look at what is, but what could be. This leads us to an outlandish idea, a concept as bizarre as it is intriguing: the white hole. Imagine a black hole running in reverse. Instead of swallowing everything in its vicinity, it spews out matter and energy with unrestrained fury. A cosmic geyser, erupting into existence rather than a drain down which everything disappears. This is the essence of a white hole, the theoretical time-reversed counterpart to a black hole. Where a black hole allows nothing to escape, a white hole allows nothing to enter. Imagine a region of space that relentlessly pushes away any and all matter, defying gravity's embrace with an unstoppable force. It's as if nature decided to create a cosmic bouncer, permanently stationed in a region of space, allowing nothing inside. The very thought is perplexing, as every single object in the universe attracts every other object in the universe. What defies this basic rule? White holes first emerged as mathematical solutions to Einstein's field equations of general relativity, the same equations that predicted the existence of black holes. Just as a coin has two sides, these equations seem to suggest that black holes might have a mirror image, a region where time flows in the opposite direction. However, the mathematics were one thing, and the physics was quite another. While these equations are valid, they are not guaranteed to be physically possible. While black holes seem to be abundant throughout the universe, backed up by decades of observational evidence, white holes remained stubbornly theoretical, elusive objects that stubbornly refuse to show their face in the real cosmos. In fact, the very existence of white holes challenges our fundamental understanding of causality, the principle that cause must precede effect. Think of a black hole as a cosmic drain where matter and energy flow inexorably towards the singularity. Now, imagine reversing that flow. Matter and energy would have to be ejected from the singularity, seemingly violating the arrow of time. How could something emerge from a point of infinite density, from a place where space-time itself ceases to exist? It is akin to a river flowing uphill or a fire creating its own fuel. This inherent violation of causality makes white holes extremely problematic from a physical standpoint. They seem to require a level of fine-tuning and exotic conditions that are simply not observed in the universe. They are often regarded as mathematically possible, but physically implausible. Adding to the mystery is the question of stability. Even if a white hole could somehow form, it is unlikely to remain stable for very long. Any attempt to add matter to a white hole would likely cause it to collapse, transforming it into a more conventional black hole. It is as if the universe itself is conspiring to prevent these objects from existing. Despite these challenges, the theoretical links between black holes, white holes, and wormholes continue to fascinate physicists. Remember the Einstein-Rosen bridge, that theoretical tunnel connecting two distant points in space-time? Some physicists have speculated that a black hole might be connected to a white hole through such a wormhole, providing a potential pathway for matter and energy to escape from the black hole's interior. It's akin to one cosmic magician's entrance being another's exit. While the interior of a black hole is a vast unknown, could a white hole hold some clues? This idea has fueled countless science fiction stories, but it also has some basis in theoretical physics. However, there is no plausible means for a human, planet, or spaceship to travel through this wormhole from a black hole to a white hole. One of the biggest stumbling blocks is the inherent instability of wormholes. As we discussed earlier, they tend to collapse almost instantly, pinching off the tunnel before anything can pass through. Furthermore, the extreme tidal forces near a black hole would likely tear apart any object before it even reached the wormhole's entrance. Even if a stable wormhole could be created, the journey through it would likely be a one-way trip. The laws of physics, as we currently understand them, would prevent any object from traveling back through the wormhole from the white hole to the black hole. So, while the idea of a black hole connected to a white hole through a wormhole is intriguing, it remains firmly in the realm of theoretical speculation. There is no observational evidence to support it, and there are significant theoretical challenges to overcome. But can white hole physics offer any clues about information escape or the ultimate fate of matter inside black holes? This is a question that has been debated for decades, with no clear consensus emerging. Some physicists have suggested that white holes might provide a way for information to escape from black holes, resolving the information loss paradox. The information that gets sucked into a black hole could come out via a white hole through a wormhole. However, this idea faces several challenges. First, there is no evidence that white holes actually exist. Second, even if they did, it is not clear how they could preserve and transmit information without violating the laws of physics. It's a bit of a mystery, on top of another mystery. Despite their theoretical nature and lack of observational evidence, white holes continue to intrigue physicists. They force us to question our assumptions about the nature of space, time, and causality. They push us to explore the boundaries of what is possible and to develop new theories that can explain the universe in all its strangeness and wonder. Could they somehow reveal the secret to the information paradox, that cosmic puzzle that has had some of the greatest minds on Earth stumped? But even as we contemplate these mind-bending possibilities, the birth of universes within black holes, the existence of their time-reverse twins, and wormholes connecting to every point in the cosmos, remember that a large amount of this is still theory. How do we distinguish fact from fiction? How do we test these wild ideas? The answer, as always, lies in observation, in pushing the boundaries of what we can see, hear, and measure. So what does the future hold for black hole hunters? What new tools will we wield in our quest to unravel the secrets of these enigmatic objects? The next generation of telescopes promises to revolutionize our understanding of black holes, providing sharper images, more sensitive detectors, and new ways to probe the extreme physics of these regions. It's not just about building bigger telescopes. It's about developing new technologies, new techniques, and new ways of thinking about the universe. Consider the Event Horizon Telescope, that remarkable network of radio telescopes that captured the first ever image of a black hole's shadow. Now imagine an even more powerful Event Horizon Telescope, with more telescopes located in even more remote locations and operating at even higher frequencies. This next generation EHT, the Next Generation Event Horizon Telescope, will not only provide sharper images of black hole shadows, but also allow us to study the dynamics of the accretion disks in much greater detail. The telescopes will allow us to see the infalling gas follow matter as it approaches the event horizon and to witness the launching of powerful jets. It's like watching a cosmic ballet in real time, witnessing the intricate dance of gravity, magnetic fields, and matter near the edge of oblivion. But that's not all. New optical telescopes, both on the ground and in space, promise to provide unprecedented views of the universe. The extremely large telescope, currently under construction in the Atacama Desert of Chile, will be the largest optical telescope ever built, with a mirror 39 meters in diameter. The 30-meter telescope, which is an upcoming extremely large telescope planned for construction on Mauna Kea in the state of Hawaii, but has plans of being built on La Palma in the Canary Islands. These telescopes will be able to observe the faintest and most distant objects in the universe, including the galaxies that host supermassive black holes. This will enable us to study the relationship between black holes and their host galaxies in greater detail, to understand how these objects co-evolve over cosmic time. It's as if we are finally receiving the glasses we've needed to see the most ancient secrets of the universe. And what about gravitational waves? Those ripples in space-time that are revolutionizing our understanding of black holes. The current generation of gravitational wave detectors, LIGO and Virgo, have already detected dozens of black hole mergers, providing valuable insights into their masses, spins, and distributions. But even more sensitive gravitational wave detectors are on the horizon, promising to detect even fainter and more distant signals. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave observatory that will be sensitive to much lower frequency gravitational waves than LIGO and Virgo. It will be able to detect the mergers of supermassive black holes, the collisions of galaxies, and even the faint whispers from the early universe. Think of LISA as a giant cosmic ear, floating in space, listening to the deep rumbling sounds of the cosmos. Can you imagine how clear the symphony of the galaxies will be to our instruments when there isn't even atmospheric interference? These future instruments promise to detect fainter or more distant black hole signals, probing the universe to greater depths and revealing objects that are currently hidden from our view. They will allow us to test fundamental physics, pushing Einstein's theory of general relativity to its limits and searching for evidence of new physics beyond the standard model. What if those black holes are not only more plentiful than we thought, but also possess properties that we had never considered? And these upcoming observations could also constrain theories about black hole interiors, helping us to solve the information loss paradox and to understand the nature of quantum gravity. The deeper our gaze, the more fundamental shifts to our existing knowledge. Imagine a world where we can directly observe the quantum effects near the event horizon, where we can map the complex structure of space-time around a singularity, and where we can witness the birth of a new universe within a black hole. It sounds like science fiction, but it may be closer than we think. We could have the ability to see a quantum version of gravity in action. But the exploration of black holes is not just about building new telescopes and developing new technologies. It's also about fostering collaboration, sharing data, and training the next generation of scientists. The quest to unravel the secrets of black holes is a global endeavor, one that requires the combined efforts of researchers from all over the world. It's a true cosmic partnership to unlock the universe's darkest secrets. The golden age of black hole discovery is far from over. In fact, it's just beginning. Each new observation, each new simulation, each new theoretical insight brings us closer to a deeper understanding of these enigmatic objects. And as we continue to push the boundaries of human knowledge, who knows what wonders we will uncover? What long-held assumptions will be challenged? What new mysteries will be revealed? We might even discover that there are more types of black holes that do not fit our current models. There is truly no end to the amount we can learn about these dark behemoths. Even with all these technological marvels at our fingertips, even with the ability to see and hear the universe in ways we never thought possible, a central, captivating mystery remains. A question that has haunted humanity for centuries, now sharpened into a laser focus by our understanding of black holes. What's inside? We have mapped the shadows, charted the ripples, and simulated the maelstroms. We have journeyed from abstract theoretical concepts to concrete observational evidence via the Event Horizon Telescope and LIGO and Virgo. But what does it all amount to? Where does this relentless quest lead us? The truth is, for every answer we find, a dozen new questions emerge, beckoning us deeper into the unknown. Think about the sheer scale of what we're trying to understand. We are talking about regions of space-time so extreme that they defy our current understanding of physics, places where gravity reigns supreme and the laws of nature as we know them simply cease to apply. It's as if we are trying to map a land that exists outside of our reality, a realm governed by rules that are alien to our experience. What happens to information that crosses the event horizon? Is it truly lost forever, or is it somehow encoded in the Hawking radiation, like a secret message waiting to be deciphered? Or could it be, as some physicists have suggested, that the information is stored on the event horizon itself, like a holographic projection of the black hole's past? Is there a chance that it might be located in another universe? Are black holes truly singularities, points of infinite density where space-time vanishes? Or could they be something else entirely? Perhaps wormholes connecting to other parts of the universe, or even baby universes waiting to be born? And what about the event horizon? Is it a smooth, featureless surface, as predicted by classical general relativity, or is it a turbulent, chaotic region of quantum activity, a firewall of energy that would incinerate anything that dares to cross its path? Do black holes even have a boundary? Perhaps the question itself is flawed. Maybe we're asking the wrong thing. What if the interior of a black hole is not a place at all, but a process, a transformation of matter and energy into something completely different? The notion is that everything is converted to something we have no method or capacity to comprehend. After all, we are talking about something where time, space, and gravity are all operating in the extreme. What if the true nature of black holes is not to destroy, but to create? What if they are the ultimate recyclers of the cosmos, taking the remnants of old stars and galaxies and transforming them into the building blocks of new ones? Or perhaps even more dramatically, what if they are gateways to other universes, portals to realities beyond our wildest imaginations? What secrets do these portals hold? The answers to these questions may lie in a theory of quantum gravity, a theory that can reconcile general relativity with quantum mechanics, a theory that can finally unlock the secrets of the singularity and the event horizon. It is possible that the quantum world, too small for humans to comprehend, and gravity, too large for humans to see, may work hand in hand to produce these complex cosmic entities. String theory and loop quantum gravity offer tantalizing glimpses of such a theory, but they also face significant challenges. Which approach will triumph? Which will offer us the answers we seek? The question of which one is the key to unlocking the secrets of the universe may remain a mystery for centuries. And so, the relentless quest to unravel the secrets held within black holes continues to drive scientific innovation and push the boundaries of human knowledge itself. From the pioneering work of Einstein and Schwarzschild to the groundbreaking observations of the Event Horizon Telescope and LIGO and Virgo, we have made incredible progress in understanding these enigmatic objects. But the journey is far from over. The next generation of telescopes and gravitational wave detectors promises to provide even more insights, allowing us to probe the extreme physics of black holes in unprecedented detail. It's a never-ending quest, with the potential to reshape our understanding of the cosmos forever, a pursuit driven by curiosity, wonder, and the insatiable human desire to know what lies beyond the veil. Where will this ambition lead us? Only time and a whole lot of scientific exploration will tell.